Hello everyone, welcome to problem solving tutorial. This is me Mahir. Today we'll be learning things about prime numbers. So, what are prime numbers? Prime number is such a number which can only be divided by 1 and the number itself. So, prime number is such a number who has only two factors. Number 1 and the number itself. Okay, so for example, some of the prime numbers are 2, 3, 5, 7, etc. So how do we detect if a number is prime or not? Well, a naive way is to check for every number from 2 to the number -1. That means if you're checking if a number n is prime or not, then we can run a loop that runs from 2 to n-1, and we will check if any number from 2 to n-1 divides this number n. That means if there is any number such that n mod that number is equal to 0, then we will call n a non-prime number. And if there is no such number, then n is a prime number. Okay, so do we necessarily need to run the loop from 2 to n-1? No. Let's think about any random number, say 25. The 25 is for sure, well, let's talk about 32. The 32 is for sure not a prime number, since it's an even number, so at least it is divisible by 2. Okay, so what are the numbers that can divide 32? That means what are the factors of 32? There are 2, 4, 2, 4, 8. Okay, so 2, 4, 8, 16, and 32 itself. Well, there is one also. Since you're only counting numbers lesser than 32, so we'll be taking into account only these 4 numbers. As we can see, the highest number that can divide 32 is equal to half of 32, and it can't be greater than 32, because let's think about it. Any number which is greater than half of 32 can never can never be factor of 32, since even if it is multiplied by 2, for example 17, which is 1 more than the half of 32, if we multiply it by even 2, the lowest number, then we will get 34, which is greater than the 32. So if we run the loop up to n by 2 and check if any number divides n perfectly, we can find prime number. Okay. Now another thing. Let's take a look for 32. Let's take a look at the factors of 32. As we can see, well, let's work with 64. We are checking for 64 now. For 64, as we can see that there are 2, 4, 8, 16, 32. These are the numbers that divide 64 perfectly. Okay, now let's think about it. Here, well, let's go with another example just to clear the concept. Let's think about 30. Okay, for 30, the dividers are 2, 3, 5, 6, then 10, 15. Okay, we are checking for 30. Okay, now if we take a look at this, we will see that at first there is 2. Let's just recap. Till now we are checking up to n by 2 to check if a number n is prime or not. We are checking up to n by 2. Now here, let's come here. Okay, so here we can see that 2, 3, 5, 6, 10 and 15 divides 30 perfectly. That means they are the factors of 30. Okay, here we cannot get 2 from any of the previous numbers. No matter what operation we make on the previous numbers, we won't get 2. By any type of multiplication, we won't get 2. Same goes for 3, same goes for 5. But here is the thing. For 6, however, we can get 6 by multiplying 3 and 2. These 3 and 2 were previously found factors of 30. Same goes for 10. We can get 10 by multiplying 5 and 2. We can get 15 by multiplying 3 and 5. So as we can see, a great difference lies between these two parts. We can get these numbers from any of the previous numbers, but we can get these numbers by multiplying some of the previous numbers. So what actually is happening here? Well, here is the thing. As we can see, the square root of 30 is, okay, where is the square root sign? Okay, the square root of 30 is 5.47. If we truncate it to round it to its nearest integer, we will get 5. So 5 is actually the integer. Well, its 30 square root is actually 5.47 something. But approximately, if we take 5, then we can see that any number, any factors of 30 that are greater than the square root of 30 can be found by multiplying any of the previous factors. That means for 30 the square root is 5.47 to be precise. So any numbers greater than that square root can be found from the previous numbers by multiplying some of the previous numbers. For example, 6 can be found by 3 into 2. But any numbers lesser than or equal to the square root of 30 can never be found by multiplying any of the previous numbers. That means to check if 30 is prime or not, we can just run loop up to the square root of 30. If at first we will check for 1, then we will check for 2. At first we will check for 2 since 1 is factor of any number. At first we will check for 2. Since we are getting a hit, we will call it a prime. If it was not divided by 2, then we will have checked for 3, then 4, then 5, and then we will stop checking. Since any number greater than 5, that is the square root of the number we are checking for, since we are in this case we are checking for 30, any number lesser than or equal to, greater than 30 square root can be found by multiplying the previous factors. So we don't need to check for 6, 10 and 15s, because if they are factor of 30, then, well, we are checking whether a number is factor of a big number or not, just to make sure that number is prime or not. But since before checking for 6, we'll get hit at 2 and 3. Since 6 has factor 2 and 3, before coming to 6, we'll find out if 30 is prime or not. We don't need to check for numbers greater than square root of 30. I guess it is clear that if you're checking whether a number is prime or not, we just have to check up to the square root of that number. So we can replace this n by 2 to square root of n. So if we run a loop that goes from 2 to square root of n, and if we don't find any number such that n mod that number is equal to 0, then we will call n a prime number. Means for I equal 2 to square root of n, we'll check if n mod I equals 0, then n not prime. If we don't find such a case, then we will call n a prime. So here is the thing. This is a basic optimization to check if a number is prime or not. That takes square root time. Okay, so that's really works fine. We are getting the status of a number just by checking square root of that number, and we are getting the result. But here is the thing: what if we are continuously getting, queries of different numbers, and we have to give output whether it is prime or not? Say for example, we will be given any numbers from 1 to say 10 to the power 6, and we have to say if it's prime or not. That seems like very huge work, since we have to run a loop for each of those. Well, there can be any numbers, and for each number we have to calculate, we have to run this algorithm, and we have to check if it's prime or not. So even if we keep track, even if we store the result for a particular number in an array, still in worst case we have to check for 10 to the power 6 times. If there are 10 to the power 6 different queries, then for each of those numbers we have to run this loop and find out if that is prime or not. So it will take a huge time, and surely your code will get time limit exceeded verdict. Since, I guess you get the point. So what should be our approach? What we can do is, we need to use sieve of Eratosthenes. This is basically a technique to find prime numbers from 2 to a very large number. Let's say the number is 10 to the power 6. So what will be our approach? What our approach will be is that we will first generate all the prime numbers that are in the range from 1 to 10 to the power 6. We'll keep those status in an array. Then whenever we are getting any query, we will just check the array and see whether it's prime or not. So that's okay. But how do we do this pre-generation thing? How do we pre-generate the array? Because if we run this loop for every single number, then it's gonna take 10 to the power 9 iterations to calculate if a number is prime or not, in worst case. So this is not a good approach. So we have to think of something. So what do we do? Well, before going into coding, let's take a look at this. Okay, so here are some numbers from 2 to 50. Well, I guess you know that 1 is not a prime number, since 1 can only be divided by just one number, 1 itself. And in order to be a prime number, a number needs to have 2 and only 2 factors. Okay, so here are some numbers from 2 to 50. So initially they will all be counted as prime numbers. What we will be doing in our algorithm is, at first we will take a prime number, then we will mark each and every one of its products as non-prime. Since each and every one of its product is not a prime number, since they all have our starting number as their factor. For example, if we start with 2, since 2 is not marked yet, so we will take it as our prime number, and we will mark each and every one of its products as non-prime. Here is how we did that. 2 is our unmarked number, so we'll take it as prime and we'll mark each and every one of its products as non-prime. So 4, 6, 8, 10, 12, 14, 16 all will be marked as non-prime numbers. Okay. Then we will go to the next number. The next number is 3. So we'll again take 3 as prime number and we will mark each and every one of its product as non-prime number. Here is what's happening. We are taking 3 as prime number and we are marking each and every one of its products as non-prime number. And we will do the same thing. Okay, now we will come to 4. Here is the thing. When we are at 4, we will find out that 4 is already marked as non-prime number in one of the previous steps. 4 is already marked as non-prime number. So we will not continue this procedure for 4 since it is already marked as prime number. So we will skip that 4. We will skip it and we will go to 5. Since 5 is marked neither by 2 nor by 3, we will start from 5 and we will mark each and every one of its product as non-prime number. Okay, here what we are doing is starting from 5, we will take 5 as prime number and we will mark each and every one of its products as non-prime. So far we have marked all the non-prime numbers that has 2, 3 and 5 as factor. So here is the thing. As we can see that 6 is marked twice for 2 and 3. 10 is marked twice for 2 and 5. In the same way 15 is marked twice for 3 and 5. So these are all redundant markings. How do you get rid of this? How do you reduce this redundancy? Maybe we can't get rid of this totally, but we can reduce the rate of this overlapping marking. So how do we do that? Okay. So how do we reduce this redundancy? Well, if you take a look at this, let's start with 3. Since 2 has a very low rate of difference between each of its products, so let's start from 3. As we can see, while we are marking 3's factors, the first factor we get, 6, is already marked. The second factor we get, however, is not marked before. So what is the relation between this previously non-marked factor and 3? Well, this is square of 3. Okay, so if we start, and same goes for 5. 5 has first factor as 10 and it is already marked. Second factor of 5 is 15. It is 2 already marked. Then the next factor is 20. This is also marked previously. The next number, the number that is not marked already, is 25. And what is the relation between 25 and 5? 25 is square of 5. Same goes for 2. If you take a look at it, 4 which was the first number which hasn't been marked yet, is actually square of 2. So I guess you have understand what I'm trying to say. That is, if you start from square root of a number, then we will reduce some of the redundancies. for 5 there could have been, well, 3 redundant marking, and we can avoid those if we start from 25, that is square of 5. Okay, so what we have learned is to start marking non-primes, we will start from square root of a number. I'm sorry, square of a number. So for 3 we will start from 9, from 5 we will start from 25. Okay, now here is another thing that we need to take a look at. Again, we won't be talking about 2 just yet. Okay, for 3, let's take a look at 3. For 3, okay, fine, we are starting from 9. But where do we go after 9? 12, and 12 is already marked. Same things happens for 25. Why do we go after 25? We go to 30, which was previously twice marked. So, starting from 9, what is the next number that is not marked yet? 15. Starting from 25, what is the next number that isn't marked yet? 35. So what is the relationship between 15 and 9? 15 is 2 into 3 unit greater than 9. That means if we add 9 plus 2 into 3, we'll get another number which isn't marked yet. Same thing happens for 35 and 25. If we add 25 plus 2 into 5, then we will get 35, which is previously unmarked factor of 5. So what we have learned here is, while previously we were incrementing by 3, 3, 3 or 5, 5, 5, we will be incrementing by 2 into 3, 2 into 3, 2 into 3, or 2 into 5. Okay, from 25 to 35, 2 into 5 that is 10, then 2 into 5 that is 45. Okay, as you can see, still we are getting overlapping at 45, but it is reduced by a huge rate. So what are the 2 things we have learned? That to start the marking of the prime numbers, we'll start from a number, and if that number is a prime, then we will take that as prime number, and we will start, initially all the numbers will be marked as prime, and then we'll take a number, then we'll start marking each and every of its factors, but we will start from the square root of that number, and we will increase by twice of the previous number that we have taken as prime, and we will start marking them as non-prime numbers. So these are the 2 techniques which we will be using while our coding. So let's write it down so that we don't forget. So one technique is, let's increase the font so we can see better. So what are the things that we will be keeping in our mind? We'll go up to square root. While coding, we will check each and every one of its points. Okay, so we'll go up to square root. That means in order to check if 25 is prime or not, we'll just have to iterate up to 5. Don't need to check from 6 and so on, because if there were any factors after 6, then they would have been marked already by the previous factors. Okay, so now we will go up to square root of a number. Then what we are going to do is we will start the prime markings from square of a number. Square of a prime number. Another thing is we will increase by 2 into taken prime number. So the number we will be taking as prime number, which is marked previously, we will take that as a prime number, and then we will start from square of that number and we will increase by 2 into that taken prime number. So this will be our, and we will mark the products. So these are the 4 techniques that we will be using to complete our sieve of Eratosthenes. So that's all for today. In the next tutorial, we will be going into the coding part, and we will be following these 4 techniques and write a code that gives us a lot of prime numbers. Thanks for watching. See you in the next tutorial.